Hello. This is the second lecture of this advanced geostatistical course on spatial uncertainty assessment. And in this lecture, we'll see the introduction to geostatistical simulation methods. Okay, we have seen in an introductory course of geostatistics a large family of grading methods to achieve the most probable models of mineral resources, environment applications like characterization of contaminated sites. But in all these cases, the goal was to achieve the most probable models. Now, in some situations of natural resources with high heterogeneity and lack of knowledge, the uncertainty becomes the most important issue to be assessed. The objective of this course is precisely to characterize the uncertainty through stochastic simulation methods. Okay, the objective of geostatistical, in short, the objective of geostatistical simulation models is the integration of the concept of uncertainty in high resolution models of a physical phenomena. There's a lot of applications, heterogeneous geological environments, characterization of petrophysical properties of aquifers, oil and gas reservoirs, and so on, and also in environmental risk evaluation. So let's see the a difference between the estimation methods that you have learned before and the simulation. And let's take a very simple example of a histogram. Suppose this is a histogram of a porosity values. Now, my question is the average value sufficient to represent the knowledge of a given variable, in this case porosity, or permeability, or grade, or polluted concentration? And the straight answer is depends. Depends on the variability, the variance of our variable, depends on our knowledge or our ignorance about that. Okay? The same way, let's see for example, now applied to a model, a image obtained of our reality. In the top of this picture, you can see the estimation model, which is a typical output of a grid map, smooth version of our reality. This is the most probable model of our reality. The simulation models do not give this just one image, but a set, an ensemble, 100, 1000 images, equiprobable images of that reality, but with the same variability and spatial continuity as revealed by our experimental data. Okay. Now, the simulation models, this ensemble of realizations are appropriated, as you are going to see, appropriated for the characterization of very heterogeneous properties and environments. High variability, like porosity, permeability, soil contaminations, fractures, and so on. Now, let's see how we can extract the uncertainty from those simulated realizations. And take one case is, look at this. If you have 100 realizations, for example, 100 models, simulated models, take this pixel here. And you are going to take from those models the value, 100 values of that specific pixel. And you can build the most rich tool to characterize the uncertainty of this pixel, which is the histogram of probability distribution and so on. Okay. The same way, we can also evaluate the concept of spatial uncertainty, not just one location, but in a given area. The joint probability of set of points of that area to be above a given threshold or under a given threshold. Okay, and this can be taken from the local histogram, this one, of those pixels that drop in that area. Now, uncertainty can be assessed for any property of the subsoil or can be evaluated a posteriori through what we call a transfer function. Let's see what I mean by that. For example, look at one example of aquifer, the concept of uncertainty and the risk of water flow, pressure, production risk, and so on. Suppose we have a set or ensemble of simulated models of porosity and permeability. Okay, now from each pair of porosity and permeability, we run a dynamic simulator from one well to another well, we can obtain one response. But if you do the same exercise, the same dynamic simulator for all models, you obtain a set or ensemble of responses. Here it is. The uncertainty now can be measured not only on those models of the properties, but in the time response of a flow, or pressure, and so on. The same, for example, of a pollutant. The same, we can apply this. Can imagine this in a pollutant concentration for environmental risk. You characterize the models of porosity and permeability, and we run the dynamic simulation, which is, for example, the percolation of a given contamination through the soil, and you obtain the responses, the time responses of the dynamic evolution of this pollutant. Okay, and you can measure the uncertainty and risk of in all time periods. Or you can imagine, if you have the simulation, you can have realizations of metal grades in a mineral deposit, and if you apply a given production scheduling on those metal grades, you obtain the production schedule, not only the most probable, but the uncertainty of this production scheduling during a period of time. Okay. Now let's start by let's have to see how to do this to build those simulation models, and start by the simplest one: how to simulate one random variable, how to sample a random variable from its probability distributions, how to get, for example, 1,000 values from those distributions here, this one or this one, and so on. Okay, to simulate just one random variable, we are going to use the Monte Carlo method, which means that Monte Carlo is the use of random numbers to solve deterministic systems or stochastic models. And in this case, we are going to use, for stochastic purposes, I would say, to sample probability distributions. And there's two basic and most common methods. There's a lot more, but I will present you just the most common methods of Monte Carlo: the inverse transform sampling and the acceptance rejection method. Okay, let's start by the first one. Inverse transform sampling is a very simple one. Suppose we have a continuous function, which is our probability distribution, but cumulative probability distribution, for example, this one. And if that goes, for example, from 0 to 1 probability is the maximum, 1 probability. Now, so suppose that we generate one random number u, let's call u, from this interval between 0 and 1. Now, this value is uniformly distributed, which means that between 0 and 1, all values have the same, exactly the same probability to happen. Suppose it drops, I got this value here. Now what I have is to do the inverse transform to get a value of our variable that I want to simulate. If this is a porosity, I get one value of porosity. Now I repeat the process. And the next one is here, and I get this one, and so on. After 1,000 values, simulated values, I'm sure that those values follow that distribution. In the second case of a discrete distribution here, I must assure that this function here is continuous. So if the value drops in the middle of two classes, what I have to do is just an interpolation. That's it. To transform this discrete distribution here in a continuous one. This is one exercise that I suggest to you to do, which is to perform the Monte Carlo method, this inverse transform sampling, to generate values from those very simple and naive histograms with just 5 classes by using Excel. Okay. Now, let's see the second method, which is the acceptance rejection method. Okay, this is extremely simple as well, but this method has 2 steps. First of all, my probability distribution is represented by the density distribution function here, not the cumulative, but the density. What I have to do is to define an upper bound. Such a way, in any location, we have represented by this blue line a given probability. If this straight line is 1, this is the probability to be inside the distribution, to be accepted, and the red to be rejected. This one in details of the right tail of the distribution, we have this blue straight line to be accepted and this red equivalent to this red to be rejected. Now, the method is very simple, consists in 2 steps. As I said, I generate one value here, this one, x1. This is value of porosity. Now this value in the second step will be accepted or rejected. And this value has this probability to be accepted. Suppose the random number, the second random number, drops in this blue area, the value is accepted, and the same for the other one, and so on. If this acceptance and rejection method goes on until I get the number of simulations I intend. There's a lot of algorithms to generate continuous random variables that from very known and parametric distributions. I don't go through them. I just present. This is those algorithms are how to do the inverse transform. After you generate the random number u, how to get the value from a uniform distribution, from exponential distribution, from a standard normal, a Gaussian distribution, but standardized Gaussian distribution. There's several methods. I put just here 2 methods. Okay, log normal, triangular, and so on. And this is for the empirical, any empirical distribution. But I would like to slow down a bit from one very, very particular case. That, for example, when you have a set of values, for example, 20 values of porosity of a soil, and you want to generate realizations, you have to generate simulated values from those from the histogram or distribution of those 20 values. Okay, let me tell you that if you have 20 values, we can assume that each one has equal probability to occur, which is 1/20. Okay, those are the values, the porosity values. Now, the first thing we have to do, we are going to build a kind of cumulative distribution, of cumulative histogram. And we do the rank ordering, okay, of those values from the minimum to maximum. Okay, this is the same but rank ordered of porosity. Now you can build the cumulative probability. The first one has 1 over 20, 2 over 23, 4, blah, blah, until 1. Okay, this is the cumulative distribution. Now, to generate, to run to run the simulation, the inverse transform method, you generate one random number from 0 to 1, and if it drops here, for example 0.45, the porosity value to be simulated is 0.3. But if it drops in the middle, you can do a linear regression between those two values. Okay. Now let's see another particular case, which is a categorical variable, not a continuous but a categorical variable. Okay, if, for example, if you have lithoclasses of rock, clay, sand, and so on, and you have 3 lithoclasses. The first one represents 25% in a given area. The second one 40%, and third one 35%. It sums up to 1. Now, the first thing that you are going to see is to create a pseudo-cumulative distribution. Why is pseudo? Because there's no order relation. You can put the sand first or clay first and so on. We choose the small one. This is lithoclass 1. The second one, you sum up 25 to 35, and the other one 40%. Okay? Lithoclass 2, sorry, and lithoclass 3. And the procedure is the same. Generate one random number. If the random number drops between 0 and 0.25, it is generated the first lithoclass. Remember, this is a categorical variable. There's nothing in the middle, okay? There's no interpolation. If it drops here between 0.25 and 0.65, it's the second lithoclass, and otherwise it's third lithoclass. Now, we have seen how to generate several realizations from one distribution, okay, one variable. Now, but normally we do not. There's just few applications to simulate just one variable, but it's most common, for example, if you have a system with a set of independent variables. Let's see, for example, in a mine operation, we have 4 operations. For example, load the truck in one place, the full truck is transport the mineral until other point, unload the truck and come back. Okay. Suppose we measure in each of the 4 operations, we measure the histogram of the time that it takes to load the truck. And the histogram is represented to load the truck. The cumulative histogram is right here. The transport is more fast, takes less time. Okay, the abscissa is time, and the time for unload, and the histogram of time to return. Okay, now we run the simulation as they are independent. You can run first and second independent of this one and so on. So you generate one random number, and the first time to load truck is T1. The same cycle, the time to transport identically is T2, the time to unload C3, C4. Run again, and you obtain another set of those four times of this operation. So you can, at the end of 100 simulation, 1000 simulation, you can give a total time of all cycle T1, T2, T3, Tn. Okay, and this total with those 100 values of total time of the entire cycle, you can build a distribution. And for example, this is a very naive example, just to transport one given tonnage from one place to another, you can compute this histogram of the time, and you can also evaluate the probability of exceeding the shift time. What is the probability to exceed, of not accomplish the objective of transport that tonnage? Okay, this is the risk of not accomplishing the objective to transport the tonnage. This is a simple example, but you can imagine more complex examples of independent variables. Okay. For example, another, which is the simulation of fracture network. This is the front of a marble quarry. You can measure, you can, from this front here, you can measure the fractures, the direction, the length, how many segments each fracture is composed, and so on. And you can represent the histograms of those of those variables. For example, orientation, length, number of segments, 3 variables. Suppose they are independent, so you can simulate separately. You generate one value from the orientation, okay, one value from the length, one value from the number of segments, and you represent here, okay. And you can obtain, for example, images of the fracture network for several realization, how many realizations, so on. And this is important. Sometimes it's an important tool just to evaluate the risk for the exploitation of the marble quarries, to take the right dimension of the blocks and so on. This is the second exercise that I would like to suggest you, is the simulation of a set of independent random variables by using Monte Carlo. Suppose, what is the problem? We have to forecast the total number of days to drill a given well. The well is supposed to cut 3 different geological formations, which means that they take different times, okay? Previous wells, for example, 11 wells at the same region, gave the drilling temporal duration in each formation, okay? And formation 1 is in column B, formation 2 is column C. This is can be represented in Excel, okay? Now, what we want is to calculate. I want you to calculate the total time based on the average of each formation temporal vectors. Okay, so calculate the uncertainty and risk, probability to exceed 21 days, probability to exceed 23 days, and etc. in this operation of drilling a well. This will be given in practical classes. Now, let's jump to a little bit more complex situation. I want to simulate 2 dependent random variables. Let's suppose that one wish to simulate pairs of porosity and permeability values that show a positive correlation. It means that, for example, this is a B-plot of values taken from experimental samples of porosity and permeability, okay? And we want, at the end, when I simulate porosity and permeability, we want they reproduce this, this joint distribution. Okay, I do not want it reproduces values here. They do not exist in reality. So they must reproduce this kind of behavior. Okay. So in order to do that, to simulate two dependent random variables, we are going to follow the principle of sequential simulation. We are going to apply the Bayes law in sequential steps. For example, if we want to the bivariate distribution is equal to the the product of a marginal distribution of z1 plus times the conditional distribution of z2 given z1. This is a classical rule, Bayes rule. So to simulate the pair of values here in those this distribution means that is equivalent to generate one value from this one, okay, the marginal distribution of of first variable, and you know to do that by inverse method, and after it generates z2 from the conditional distribution of z2 given the value, previous simulated values. Okay? Let's see the illustration of what I meant with that. So the first, suppose we have to simulate porosity and permeability, and suppose this is the cumulative distribution of permeability, okay? And I simulate by inverse transform the first value of permeability using Monte Carlo, okay. Z1. Now I'm going to the total bivariate distribution of porosity and permeability. This distribution can be obtained for the experimental samples, and I'm going to extract the conditional distribution of all values, this green area, all values of porosity given the preview values of permeability. So I do not going to use values of porosity on this side, but just from this slice, which is the conditional distribution. This conditional distribution is here. This marginal is this distribution here of porosity, and after that I just generate the value of porosity from this distribution here. Okay. So I am sure after this that Z1, this value of permeability, and Z2, the value of porosity, belongs to this B distribution here. This is the way how to simulate two dependent variable. Now let's recap a bit about what is this conditional distribution is about. For example, take the two variables v1. This is a simple example, v1 and v2, 100 values of v1 and v2 represented in those classes of v2 and those classes of v1. This is absolute frequency of our variable. Okay, so we can convert this absolute to relative frequency by dividing by 100, which is the number of samples here. Okay, now the conditional distribution is not by the same formula that we have seen before. This conditional distribution of v1 given v2 is no else than the B distribution over the marginal distribution of v2. For example, if we want to know the distribution, the conditional distribution of v1, this one here, given the first class of v2, for the first class of v2, the first thing that we have to do is just to calculate the total frequency of this class, which is for v2 equal 4, which is 0.19. Okay, this one. Now applying this formula, we obtain from this line here, okay, this row, we obtain now the conditional distribution by dividing those values by 0.19, which is those ones. Now they sum up to 1. Okay, this is a classical. Now, for example, to simulate a pair of values of two random variables, v1 and v2, for a histogram. Now, first, we generate by Monte Carlo, we generate one class of v1, and suppose it drops the class v4, the fourth class of v1. Now I take the values, the conditional distribution, those values of v2 given v1, and I represent here. This is the histogram. Now I generate a value from this histogram of v2, and I'm sure that those two v1 and v2 just simulated values are they represent this B histogram, B distribution, sorry. Now, simulation of two pairs from the acceptance rejection method. This is exactly the same. Generate one class of V1. First the class of first the fourth class of V1 and one class of V2 here, and we gives you this value, and we calculate this probability, and we accept or reject. This is exactly the same. Okay. Now, applications. Let's see the simulation of fraction networks with dependent variable that fall. Now, this is the most real. That the other one that we assumed independence. That we assume that the length and orientation have some relationship according this B distribution here. Okay, so we can just do exactly the same procedure. We first generate the orientation, one given orientation. Afterwards, we go to the conditional distribution of lengths given the first simulated value of the orientation, and extract those two simulated values. Length orientation can be represented here in this fraction network. Now let's move to our main goal: how to simulate independent random variables. This is how to simulate this multi-distribution f z1, z2 until zn. Okay, following the same rule, Bayes' rule, this is equivalent to simulate a marginal distribution from marginal distribution of z1, one value from this. Generate the second value of this conditional distribution of z2 given z1, the third z3 given the previously simulated values, etc., 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 until I simulate the n values. And I'm sure at the end that at the end we obtain, we generate a set of this multi variable distribution that follows this distribution here. So let's move a bit to the geostatistical framework, the random functions framework. Do you remember in the first introductory course that we assume that in any sample location, the value that you get at any sample location is assumed to be a random variable from which we know just one value, which is the sample, the experimental value. At any sample location, we represent this n sample location with another random variable, which we do not know any value from them. But there's just one condition: those random variables are just correlated to each other. They have some correlation, so giving rise to what we call a random function. Is no else a random function that a set of dependent random variables. Now, and we have you have learned this in the introductory course. And suppose now we represent in 2D our field, our area, and in this area we represent this continuous area by a discrete grid of points. Okay, this would say 64 points here. But from those 64 points, we know 5 sample values. Those ones here: 1, 2, 3, 4, 5 sample values. Okay. So the point, the objective is how we do. If we know the reality there, those five values, we do not simulate them. We do not need, because as you are going to see afterwards, the simulation models reproduce reproduce our experimental data samples. So we do not simulate those values. So what we wish is, for example, now in the first step is to simulate this point here. It was chosen randomly in the entire grid. Let's call Z6, but when we want to simulate Z6, the value of our variable, for example, porosity, permeability, and so on, let's call it, we want to simulate the value at that location given the knowledge of Z1, Z2, Z4, Z3, Z4, Z5. Okay, this conditional distribution. Okay, if we obtain this conditional distribution, we generate one value, and here it is, and we get the Z6. Now, sorry. Now we are going to move and to generate the other value, Z7, but conditioned to one more value, Z6. Z1, Z2, Z6, Z5, Z6. And so on, and so on. And we move to another random location, Z8, and so on. Okay? That's the procedure, the basic procedure of the simulation. The simulation of independent variables in the framework of, in the geostatistical framework. Okay? But here is a problem. What is the problem? This method is quite simple, following the Bayes rule, but the problem is how to obtain those conditional distributions. For example, here we have 7 samples. We choose random the X8 location, and the idea of getting this conditional distribution here is to obtain this conditional distribution based on the previously known values Z1 to Z8. Okay, and we have to imagine a method to estimate this conditional distribution through the known values around. Okay, this is the idea of sequential the sequential simulation algorithms of geostatistical sequential simulation algorithms is to obtain the local CDFs, the local conditional distributions, through linear interpolation methods, simple methods like Kriging, not just to obtain the average value that you got in your previous course, but to obtain the distribution. Okay, and we are almost there. So we move to, we generate this value, we move to another one. It's always the same procedure. We randomly choose and we estimate the local distributions and so on. Okay. Now, can you see? We are going to see a very simple example. The sequential simulation of categorical variables, three little faces, the same ones that you've seen, T1, T2, and T3, represented by three colors here. Okay, we choose one location here, okay, and now, as you have seen, to build the conditional distribution is very simple. It's just to estimate the probability to belong to little class 1, little class 2, and little class 3. This can be made, for example, that one method that you have learned with the indicator kriging. With the indicator kriging for categorical variables, you can calculate. For example, you calculate for the probability to T1. T1 is the red, higher is 60%. Probability to T2 is green, is 25, and the other is 15%. Okay, it sums up to 1, and afterwards, in second step, we build. For that location, we build this pseudo-cumulative distribution. And we generate one value from one random variable, and for example, if the random number, is less than 0.6, then in this point takes the little class 1 at the point between 0.6 and 0.85. It takes the little class 2, and otherwise greater than or equal to 85%, it takes the little class 3. And that's it. For example, suppose you got the red one, we move to another one. When you move to another one, we build again. But in this case, the most probable little class is the second one. You see, it's more close to green. So and the equivalent pseudo-cumulative distribution is 1. And you repeat the process, simulate until all grid nodes are simulated. Okay, now let's summarize. Stochastic simulation, sequential simulation, or geostatistical sequential simulation is based on two fundamental steps. First, we must estimate the local distribution functions, and in the second step, we generate one value from those conditional distributions. We simulate realizations by Monte Carlo. And as you are going to see, the sequential procedure is performed in order to preserve the main properties of the spatial simulation process. Spatial variability, it will be reproduced, the variograms, and also the histogram, the distributions, and also honoring the experiment data sample values. Okay. So this as I said, these methods are based on those fundamental steps. They make the local CDF, generated values from the local CDF. Now, in the next lectures, you are going to see the methods for simulation of continuous variables. In the last lecture, you see a method to simulation, stochastic simulation or spatial simulation of categorical variables. Depending on the methods you use to estimate for the first step the local CDF, we can have the sequential indicator simulation, where we use indicator formalism to estimate local CDFs. We have the sequential Gaussian simulation, we are going to see that, where we use the multi-Gaussian kriging to estimate local CDF, and you have direct sequential simulation, which do not imply any transformation of original variable. Okay.